Hi everyone. In the previous lectures, we started our discussion on single stage MOS amplifiers and we finished our discussion on common source amplifiers. In this lecture, I will introduce another single stage MOS amplifier configuration called the common drain configuration. But before that, I'll just clear a few concepts or ideas about the power delivered to the load and power taken in from the input. So shown here is a general amplifier structure. So it's a general amplifier model. We have an input with a finite source resistance which is AC coupled through a capacitor C and a load which is AC coupled through a capacitor C again at the load side. Now typically the power, I've given you an example, a load here which is modeled as a load resistance can be an audio amplifier where you may have to deliver few watts of power, an amplifier may have to deliver few watts of power, or it can be an antenna in a cell phone where the power delivered will be in the order of few, probably less than a watt, a fraction of a watt. So the job of an amplifier is to actually draw little to no power from the input but deliver a finite power as desired by the load at the load side. Now we know that the input power is limited to a maximum value given by Vs squared by 4Rs. So if from that comes from maximum power transfer theorem. If you have a voltage source with source resistance Rs, it cannot deliver a power greater than Vs squared by 4Rs. Now we need to build, the job of an amplifier is that of course this may not be sufficient to drive a load resistance directly. So I've given you an example. If you take an example of a microphone signal which has to drive a loudspeaker, then it cannot directly drive. A microphone will generate power in the order of milli or microwatts. So therefore it cannot directly drive a loudspeaker which will require power in the order of watts. Or for example, on your cellular phone, the microphone of your cell phone also will deliver very low power, and eventually you will have to drive an antenna, which is, of course, it's a RF power, so we have to up convert and all of that, but we can draw an equivalence to this mathematical model here and say that you have a finite power delivering source or very low power delivering source. You need an amplifier which has to amplify its power by several orders before it can deliver to a load resistance. Now we will try to analyze where does this power come from. Does this amplifier create that power out of nowhere, or where does this power that it is actually delivering to the load resistance come from? So we'll do a quick analysis before we proceed with the other single stage amplifier topology. So I thought I'll spend probably a few minutes on that topic. So what I've shown here is P out, which is nothing but VL squared by RL, that is dictated by the load power which the application demands. And the input power, this amplifier which is going to draw from the input, is denoted by P out, P in. So and the power gain of the system is the ratio of P out by P in. Now let's consider this simple common source amplifier where I've applied the input signal with some DC coupling. VGSQ is the DC voltage, Vs is the AC signal, and the load resistance here is capacitively coupled. So we know that for small signals, if you apply a small signal voltage, there is going to be a DC current plus a small signal current. Now before we begin the analysis, for the first, let's assume there is no signal present in the circuit. If there is no signal present in the circuit, there is only, which means Vs is 0, there is a DC current which is flowing in the circuit. So we have a quiescent DC current flowing in the resistor, and there is also a quiescent DC current flowing in the MOSFET. Now if you see, the resistor here, it's a passive device, so it can only absorb power. So the power absorbed by the resistor is ID quiescent square times RD. And the MOSFET is also going to absorb power because current is flowing from a positive terminal to the negative terminal, or rather the higher to a lower potential. So it's also absorbing power, and it's given by the IDQ into VDSQ. Now this is the power of your MOS device, and this is the power that is dissipated across the resistor. Now energy conservation is a very fundamental principle. It's always satisfied in many systems. So the same way, power energy or power is conserved here as well. Now this power which is dissipated across the resistor and across the MOSFET is fully delivered by the supply voltage. So the supply voltage VDD times IDQ is the power delivered by the DC power delivered by the supply. That is going to be exactly equal to PRD plus P MOSFET. So that power entirely comes from that. Now I am going to apply an AC signal. When I am applying an AC signal, what happens in the circuit here now is that I have shorted the capacitor, because also we can see that there is no average power dissipated across the capacitor. I have already discussed this in one of the previous lectures. If you take a capacitor and apply a voltage source, a sine wave across it, we know that the current waveform is going to be 90 degrees out of phase. So we can actually show that power will be dissipated in one quarter cycle and absorbed in other quarter cycle. So the average power will be 0. So the average power dissipated across the capacitor is 0. So which is why I have short circuited it, and we are not going to worry about power dissipated across the resistor or across the capacitor. Now if you see the circuit, I have shown the small signal. There is a quiescent drain current, and on top of that there is a small signal current that is riding on top of it because of the small signal input voltage applied to this MOS device. Now in all the resistors RD, if you see, there is going to be a DC drain current plus a small signal drain current that's going to flow through that. In the resistor RL, however, there will be no DC current because the capacitor would have blocked it, and you will have only AC current present. So I will call IL as the AC current flowing, IRL as the AC current flowing through the capacitor, IRD as the AC current flowing through, or I will write capital IRD as the sum of the DC quiescent current flowing through RD plus the AC current IRD flowing through the resistance RD. Then we can simply estimate the power in all these three components. So RD will be IRD square RD, I square into RD, and resistance power is also I square RL into RL, and the MOSFET power is simply given by VDS times ID. So now if you see the power that is delivered to the load, this is the useful power. This is the power that will be heard as a sound energy in case of a speaker, or it will be transmitted as an electromagnetic energy in case of an antenna in a cell phone. So this is the actual useful power which you are delivering to the load resistance. The power PRD and power burnt in the MOSFET, this is the power because of biasing. So which means you are using this MOS device as an amplifier, and that amplification doesn't come for free, it comes with an expense. So the expense that we are paying here is PRD and PMOS. So this is the power that we have to burn in the biasing circuitry of the MOS device, of the MOS amplifier. So the total power that's supplied by the supply will be equal to the power in the resistor plus the power in the MOSFET plus the power in the load resistor. So the useful power, so we define a very important parameter called the efficiency, which is the useful power, which is the power that is delivered to the load resistance divided by the total power delivered by the supply voltage. So now we see that all the power that's being delivered to the load resistance comes entirely from the supply voltage. It is the supply voltage that's actually providing that extra power, the power that needs to be delivered to the load. But you should remember, this MOS amplifier, for it to be used as an amplifier, for the MOS device to be used as an amplifier, it has to be biased in saturation region. So because of that, to keep it in saturation region, we need to burn some power. So that's the biasing power, and that's not a useful power. So if you see, the efficiency is defined as the ratio of power in the load resistance divided by the total power, PVDD. I have written PVDD as VDD multiplied by IDD. So IDD here represents the current which has a DC component and an AC component drawn from the supply. And this quantity will always be greater than 0 because it's delivering the power. This is the power delivered. So that will be, again, it will be negative because it's delivered power. This will be always less than 0. And generally, the term efficiency will always be less than 100% for any amplifier configuration. We don't discuss about power amplifiers and their efficiency in this course, but for the amplifiers that we will be discussing in this course, where we expect the amplifier to be always in saturation region for the entire input signal range. So when I'm applying an input signal and I'm expecting an amplified version of the output, in the entire input and output signal range, we expect the amplifier to be in saturation region. So such an amplifier is called class A amplifier. So where the amplifier is in saturation for the entire conduction or for the entire cycle of the input. So typically in class A amplifiers, the efficiency will be in fact less than 50%. Okay, so that's a very brief point, a very brief thing about power dissipations in an amplifier which I wanted to discuss. Just wanted to tell you that the power that's being delivered to the load resistance comes entirely from the supply voltage. It's the supply voltage that's actually giving that power. So now we'll talk about another amplifier configuration, but first I'll introduce a problem with amplifying in the presence of small load resistors. So let's say we use a common source amplifier as an amplifier. The intrinsic gain of a common source amplifier is GM/R0, which is very high. But the moment you connect it with a finite load resistance, then what happens here is that the load resistance will start loading the amplifier. And what I have shown here is actually the Thevenin equivalent of a common source amplifier. At the source end, I can write it as an amplifier with a gain of minus GM/R0 into VI. So this is VI here. At the load end, I can represent it as, it's essentially, you can represent it as a transconductor of value GMVI and an output resistance R0. So I can just convert this into an equivalent Thevenin voltage, which will be GM times R0 into VI with a minus sign, and a Thevenin resistance of value R0. Now if your RL is much smaller than R0, the gain reduces significantly from its supposedly nominal value of A0, which is the intrinsic gain value GM/R0. It reduces significantly from this value. Ideally, I would want a power delivered of this type of this value, which is VI into GM/R0 the whole square by RL. This is the power I want to deliver to the load resistance. But because your load resistance is much smaller than the output resistance, most of its power is going to be dissipated across the output resistance itself. A very small power will be delivered across the load. Now, if we want to fix this problem, so I have actually shown the problem in a simpler way. So any amplifier or any circuit we know can be represented, a linear circuit can be represented by a voltage source and resistor in series with it, as far as the load is concerned. Now if your load resistance happens to be much smaller than the source resistance, then we know that most of the power that this voltage source is delivering will be dropping across the source resistance itself. Very little to no power will be dissipated across load resistance. So that's the problem. To fix this problem, we will introduce a voltage amplifier with just unity gain. So that, and also this amplifier, we need to introduce an amplifier with just a unity gain. And the input resistance of this amplifier should be infinity. And the output resistance of this amplifier should be 0. If you can introduce an amplifier of that type, then you can see that the entire Vs is going to appear across the amplifier, because if input resistance is infinity, the current drawn at the input is going to be 0. So if the current drawn is 0, there will be no power dissipated across Rs. So the amplifier is not drawing any power at all from input. So the entire voltage Vs will appear across the input of the amplifier. Now again at the output of this amplifier, because I am assuming the output resistance to be very low or negligible, this entire output voltage will be equal to the input voltage, which is Vs. So now the power delivered to the load is going to be Vs square by RL. So this block, which this amplifier with unity gain and high input resistance and low output resistance, is what we call as voltage buffer or voltage follower. Because the output voltage follows the input voltage, we call it as the voltage follower. Now we will analyze a common a MUE amplifier topology, which will emulate this behavior of a voltage follower with a near unity gain, high input resistance and a very low output resistance. And that here is a common drain configuration shown here. So in a common drain configuration, again I have said that you see where the input is C, where the output is, in the third terminal happens to be the common terminal. So in this example, the drain terminal is the common terminal. So again, I discussed when I started discussing common source, I said there are three terminals in a MUE device. So therefore I can define three common terminal topologies. The first one was common source, We saw in common source there were two possibilities and we discarded one of them. In the same way, for a common drain as well, there can be two possibilities. I can apply input at the gate. The other possibility is expect output at the apply input at the source and expect an output at the drain or at the gate. Again, this is not going to give you amplification because again, if you vary the source voltage, the drain current is going to change, but the gate current will still be 0. There is no gate current there, and so therefore even if you connect a load resistance, there will be no change in the voltage or current at the gate terminal. So therefore this I am discarding this. So the only other possibility we are left with is input at the gate and output at the source. So first we will analyze, like any amplifier topology, we will try to find the intrinsic gain, input resistance and output resistance. So first I am going to analyze for a case where channel length modulation is not there, so lambda is 0 or R0 is infinity. So we will find out the input resistance or rather we will find the intrinsic gain first under this condition when R0 is infinity. If R0 is infinity, the output node is an open circuit right now. For intrinsic gain I am going to choose load resistance to be infinity. So the output node is open. So the drain current flowing in the MOSFET is 0 because this source node is open. Now the drain current is simply given by Gm times VGS. Here VGS happens to be the gate voltage minus the source voltage. Gate voltage is Vi, source voltage is V0. So it is Vi minus V0. So we have I equals Gm into VGS is 0. So Gm into Vi minus V0 is 0. Now if you have biased your amplifier with a finite DC current, that's what is shown here, then the device is going to have a finite transconductance. The transconductance cannot be 0, which means the second term Vi minus V0 is 0, that implies that V0 equals Vi. So therefore your output voltage follows the input voltage. So it's referred to as a voltage follower. Or sometimes it's also referred to as source follower because your source node here follows the gate node or the input node, so it's also called as source follower. So first thing we have seen, the voltage gain happens to be 1. So that we said that a common drain configuration approximates a buffer. So this is the first proof which shows that it approximates a buffer. The second thing we need to see is input and output resistances. So the input resistance of a common drain configuration. So we are looking into the gate of a MOS device. So we know that for lower frequencies there is no current that's going to flow into the gate. So in fact, no matter what you connect at the load end, it doesn't really matter. The input resistance is always going to be infinity. So again, that's the second thing that we have shown today, that a common drain configuration approximate a voltage buffer in terms of its gain is equal to 1, and even its input resistance is very high, it's infinity. Now to finding the output resistance, so I'm going to short circuit the input and try to find the output resistance. Now before we analyze the output resistance, I've mentioned this in the previous class as well, now we should start analyzing the circuits intuitively. So when I apply a voltage Vi or a voltage across the gate to source terminal of a MOS device, in your mind you can picturize a current Gm times Vi or Gm times VGS flowing from drain to source. You can also include R0, but keep R0 aside. R0 is the small signal output resistance. So here you can picturize a current GMVI flowing from gate to drain to source. Similarly, if I apply a voltage between source to gate, a voltage Vi between source to gate, ideally you will have a current GMVGS flowing from drain to source. Here VGS happens to be minus Vi, so you will actually have a current minus of GMVI flowing from drain to source. Or I can just invert the sign and say that you will have a current plus GMVI flowing from source to drain. So when you apply a voltage, positive voltage, your source voltage, the AC voltage is higher than the gate voltage by say Vi volts, then you can picturize in your mind a current flowing from source to drain of value GMVI. Now this does not include the current through R0, it's only the MOS transconductance behavior. So this does not include the current through R0. So first, let's ignore R0. R0 is infinity. We are supposed to find the output resistance of a common drain configuration, so which is nothing but the resistance seen into the source terminal. So quickly we can see that even if you have a finite source resistance at the input, Since there is no gate current here, the voltage drop across RS is going to be 0, so I can simply short it. So it really doesn't matter. So the output resistance will be independent of RS, and the output resistance is the resistance seen from the source terminal. So what I can do here, I've just redrawn the circuit here. If I apply a voltage Vx at the source with respect to an AC ground, so gate is also at AC ground, so Vgs is going to be minus Vx. So I can picturize a current of value GmVx flowing from source to drain. So therefore, the resistance is going to be Vx upon Ix, which is Vx by GmVx, which is going to be 1 by Gm. So the output resistance is 1 by Gm, which is a very low value compared to R0. So if you see common gate configuration, the output resistance is very high, it's R0. But here if you see common drain configuration, your output resistance is just 1 by Gm, which is almost an intrinsic gain times lower than the output resistance of a common source amplifier. So now we have seen that a common drain amplifier satisfies all the three properties of an ideal voltage buffer: high input resistance, low output resistance, and a gain very close to 1. So now we will place this common drain amplifier in place of buffer in the circuit shown here. So you have VS-RS, a voltage source with a source resistance RS and a load resistance RL. We said that if you place this in between, then we can eliminate the problem of a high R out or high RS or a low value of RL. Okay, the problem was that a lower value of RL or a higher value of RS was creating a problem that most of the power was lost in the source resistance itself. But now I've introduced a buffer in between the source and the load. By doing so, we'll see what is the voltage that's delivered across the load resistance. Since the input resistance is infinity, the voltage at the gate is also going to be Vs. And we just said that what we will do is to analyze the circuit. I'll try to represent this part by its Thevenin equivalent. So as seen by the load resistance, I'll try to represent by the Thevenin equivalent. So for Thevenin equivalent, I'll find the open circuit voltage and the Thevenin resistance. So first the open circuit voltage, I'm going to open circuit this node. So we said the gate voltage is at Vs because the gate current is 0. So there is no drop across Rs. So the gate voltage is at Vs. And we just showed in the beginning of the lecture, if you assume R0 as infinity, if there is no R0, then we said that the source voltage will follow the gate voltage, so therefore V0 will be equal to Vs. So the Thevenin voltage here is Vs. Now next we are finding the Thevenin resistance. To find the Thevenin resistance, you will have to short circuit the input, which is what I have shown here in this circuit here. So we will have to short circuit the input and try to find the resistance seen at the source terminal. Since there is no gate current flowing through this MOSFET, there is no drop across RS, so I can short circuit RS as well. So you'll be left with an amplifier that a MOS device that looks like this. So you're looking into the source terminal for or resistance. The Thevenin resistance seen into the source terminal will just be 1 by Gm. We just analyzed that some moments ago. So you will get Thevenin resistance as 1 by Gm. Now if you see, the load resistance was previously seeing a source resistance of value Rs. But now after introducing this amplifier, it looks like a completely different source. The load now sees the same source voltage but with a very different source resistance. The source resistance is now equal to 1 by Gm, which is now under the designer's control. This 1 by Gm, Gm can be manipulated by choosing an appropriate drain current and W by L ratios. Now it's within the control of the designer. And if you see, interestingly, the Thevenin resistance has no dependence on the source resistance. It's entirely decided by the drain current of the buffer that we have added, the MOS amplifier that we have added. Now, if I write the expression for this voltage gain, it's going to be RL by 1 by Gm plus RL. It's a potential divider here, output voltage. So therefore, the voltage gain is going to be GMRL by 1 plus GMRL. If I choose your GMRL to be much greater than 1 or 1 by Gm to be much smaller than RL, then this value will be approximately equal to 1. So I've accomplished what we started out with. We started with the problem of high source resistance and we fixed it by adding a common drain amplifier in between the source and the load. So that's what I've shown here. So that's why I'm going to call this common drain amplifier as an impedance transformer or as a source impedance transformer. If a source has a finite source resistance Rs, after adding this buffer, after adding this common drain amplifier, this entire circuit is now going to look like the same voltage source Vs but with a different source resistance. So the source resistance is now transformed to a different value. So it's also an impedance transformer, a source impedance transformer. And this helps if your load resistance happens to be very small or much smaller compared to the source resistance. Now finally, I will finish the discussion on common drain amplifiers by including R0 or by taking R0 into account. So far what we have discussed so far, we analyzed the ideal common drain amplifier without channel modulation, and we also discussed what are the applications of a common drain amplifier, where is it used. So now I'll discuss about the important parameters of a common drain amplifier like input resistance, output resistance and intrinsic gain by taking R0 into account. So first, to find the parameters of a common drain amplifier, I'll find the easier ones. So there is now R0 also present in the circuit. I'll find the easier ones being input resistance and output resistance. Input resistance, since I'm looking into the gate, the current drawn is going to be 0. Even if you include R0, that current is always going to be 0. Even if you have a load resistance, the current is going to be 0. Therefore, input resistance is infinity. That remains unchanged. So this is the low frequency input resistance. That will be very high, which is equal to infinity. Now the output resistance, I have just redrawn the circuit here. You will be, again, to find the output resistance, even though Rs is present, you'll have to, when you short circuit the input, the voltage drop across Rs will be 0. So it will not really picture or figure in the output resistance calculations. So now I'm going to calculate the output resistance in the presence of R0. So now, if you look at the circuit, you can actually analyze this intuitively as well. I'll first tell the intuitive procedure and then we'll go to the rigorous standard way of solving it using KCL. If you see that you have a resistance R0 from this node to the AC ground. So I can actually redraw the circuit this way. So I can take the MOSFET R0 out of the MOSFET and model it this way. So you have R0 here. This is at AC ground. And we already analyzed, when you look into the source of a MOSFET, with gate being at AC ground and drain also being at AC ground, this resistance is 1 by Gm. So now if you look at this point, the resistance is going to be R0 in parallel with 1 by Gm. So it's R0 in parallel with the resistance offered by this is 1 by Gm. That's the resistance seen at this point. So I can directly write output resistance in the presence of R0, it's going to be R0 in parallel 1 by Gm. Or you can directly show that by writing Kirchhoff's current law at this node, at the input node. I can directly write a Kirchhoff's current law there. At the input node, we have a current Ix is the input current. That is equal to two currents. So we have GmVx, which is the current flowing from source to drain in the MOSFET, the small signal current. The other current is the current through R0. Now to measure the current through R0, we need to know the voltage drop across R0. On one side it is at 0 volts, on the other side it is Vx, so the voltage drop across R0 is Vx, so the current through that is simply Vx by R0. So the total current Ix is GmVx plus Vx by R0. So that I can write it as Vx by 1 by Gm plus Vx by R0. So this is nothing but two resistors are in parallel. R out is given by 1 by Gm parallel R0. But by now you should be able to write it directly without going through all these calculations. So the output resistance is 1 by Gm in parallel with R0. So if you include R0, it's going to come in parallel with 1 by Gm. So finally, we will find the intrinsic gain of this common drain amplifier in the presence of R0. So in the presence of R0, you will have this resistance R0 between source and drain. Now drain is at AC ground. So I will redraw the circuit. So I will model R0 from the source node to the AC ground. So this is actually drain, but since it's AC ground, I can represent it this way as well. Now all I need to do is find the output voltage V0. I know the drain current. Your drain current is simply Gm times VGS. Now VGS here is Vi minus V0. So the output voltage V0 here is simply drain current times R0. Okay. so I'll substitute drain current as GM into VI minus V naught into R naught. So you just group the terms VI on one side and V naught on one side. So we'll get V naught into 1 plus GM R naught equals GM R naught into VI. So we get V naught by VI as GM R naught by 1 plus GM R naught. Okay. So in fact, I mean, this is a very intuitively you can see that if you have a resistance R naught here and you have applied your input here, you are supposed to find the voltage at this node. You can represent this part MOSFET by its Thevenin equivalent, and the Thevenin equivalent for that is simply voltage gain is 1, so which will be VI, and with a Thevenin resistance of value 1 by GM. So we can directly write V naught as a potential divider, R naught upon 1 by GM plus R naught, which will be GM R naught by 1 plus GM R naught. You can derive it this way as well, but this is there's a brute force way of deriving it. You will get the same result. So I get GM R naught by 1 plus GM R naught, and typically the gain will be less than 1. In the presence of the intrinsic gain is going to be less than 1 if you assume a finite R naught. Okay, generally GM R naught is very high, so it will be close to 1, but it will always be less than 1. Now we will include all the loading conditions. So we are going to include the source resistance and the load resistance, and finally derive the expression for the voltage gain under loaded conditions. So what intrinsic gain is an unloaded gain. So that's a gain measured when RS is 0 and RL is infinity. So now we are going to assume all of that present, RS and RL present, and we'll try to find the gain of this amplifier. Okay, the actual loaded gain of this amplifier. So first, R naught is resistance between output node and the drain node, and since drain is at AC ground, and we can see that R naught and RL are in parallel because they share two nodes in common. So therefore I can just model R naught in parallel with RL. So that's what I've shown in this figure here. And the source resistance, really doesn't come into the picture because the gate resistance is current is 0. So no current flows through the gate. Input current is 0. Or we can also say input resistance is infinity. So no power is dissipated across RS. In fact, no power is drawn from the source itself because the current is 0. No power is drawn. So the gate voltage will be exactly equal to Vs. Now we just derived how to solve this problem. So if I have a common drain amplifier with gate voltage at Vs, the source voltage at V0, I said that you can simply Thevenize this part and represent, you can just draw an equivalent Thevenin representation for that part and simply represent it as a voltage source of value Vs and a Thevenin resistance of value 1 by Gm connected to a load resistance given by RL parallel R naught. So I can directly write the gain is going to be RL parallel R naught by 1 by Gm plus RL parallel R naught, and you get this expression Gm into RL parallel R naught by 1 plus Gm into RL parallel R naught. If your load resistance happens to be much smaller than R naught, which I said is typically the case, that's what the problem we began with in the previous lecture, in the beginning of the lecture, then this equation will reduce to GMRL by 1 plus GMRL. There are two things that you can see from this. Mainly, there are two inferences, but first inference is simpler one to see, which is there is no dependence on RS here. That's purely because your input resistance is infinity. Input resistance is infinity, so if your input resistance is infinity, you will not see RS in the gain calculations, or in your gain expressions you will not see the value of RS. Okay, only if the input resistance is finite you will actually see RS in the expression. So we don't see RS here. The second thing is that if I choose GMRL to be much greater than 1, so which means if I ensure that 1 by Gm is much smaller than RL, then GMRL is going to be much greater than 1, then this ratio GMRL by 1 plus GMRL will tend to 1, close to 1. So that's what is the other important thing I wanted to stress, is that for a voltage follower, if you want its output voltage to be independent of the load resistance, then you should ensure that for all the range of load resistance that you're going to connect to the amplifier, if your RL is always greater than 1 by Gm, then the gain will be very close to 1. Now, finally, we will discuss one application of voltage follower, which is your common drain amplifier, very commonly used in analog integrated circuits as what we call as DC level shifters. So let's say we have an AC signal. So every AC signal will have a DC signal. On top of it, you will have an AC signal riding on top of it. So if I feed this AC signal with a DC content to a common drain amplifier, the output voltage is going to be whatever the gate voltage is minus the VGSQ. The DC voltage is going to be minus VDC is the input DC minus VGSQ. VGSQ is the quiescent voltage of the NMOS transistor here. So the input peak will be same because the gain is very close to 1, but the DC value will be level shifted by VGSQ. So that will be the input DC and output DC will be different. Okay, so here we see that the level is shifted down. So the DC level is reduced here. So if I plot the DC levels, so you are going to get VDC as the input level here. Now the output voltage is same. The output peak, the AC value, the peak value of the AC signal is the same, but the DC value is reduced by VGSQ. So your VGSQ here is nothing but V overdrive plus VTN. So I said I have introduced the term called overdrive voltage, which is VGS minus VTN. So generally we can write VGS in terms of overdrive voltage and the threshold voltage as the sum of VOV plus VTN. So this DC level that's getting shifted, that will always be greater than the threshold voltage of the NMOS device here. Similarly, I can shift its level up by using a PMOS source follower. So in a PMOS source follower, input is here at the gate and source is normally at a higher DC voltage. Okay, always at a higher DC voltage. So if the device is carrying a current I0, then you need to spend the DC voltage across the source to gate will be VGSQ. Now VDC is the input DC voltage, so the output DC voltage is going to be the sum of the two DC voltages, which is VSGQ plus VDC. So that's what I've shown here. So here the DC level is shifted up by VGSQ. Okay, VSGQ. So we can shift the levels either to a lower value using an NMOS source follower or to a higher value using a PMOS source follower. I didn't analyze PMOS source follower, but everything what we have analyzed for NMOS, the same things hold true for PMOS as well. High input resistance, low output resistance, and intrinsic gain close to 1 and all of that. In fact, the small signal models for NMOS and PMOS are exactly the same. So you will get almost identical results for PMOS as well, what we have derived for NMOS. So I've just shown it pictorially here, the level shifting behavior of a common drain amplifier. So now in the next lecture, I'll discuss some problems on common drain amplifiers, and we'll try to finish common gate amplifiers as well.